Project Fire was a research project conducted under the direction of the Office of Advanced Research and Technology of the National Aeronautics and Space Administration. This project was conceived to study the thermoaerodynamics of the environment upon reentry of a spacecraft into the Earth's atmosphere at hyperbolic velocities. The research program was conducted at the Langley Research Center, Hampton, Virginia. To accomplish this experiment, a highly instrumented spacecraft was designed to withstand the severe heating and dynamic loads associated with such a reentry. This reentry package was 67 2/10 centimeters in diameter and weighed 86 6/10 kilograms. This animation shows the general configuration of the instrumented reentry package. The afterbody section of the reentry package was constructed of fiberglass with a heat protection coating of silicone elastomer containing microballoons. The front face of the package was constructed of alternate layers of beryllium and phenolic asbestos. The layered construction was utilized to ensure that the package would survive the reentry heating and would permit calorimeter and radiometer measurements to be made in a clean environment uncontaminated by products of ablation. Here is shown the beryllium calorimeter layer of the reentry package and a view of the thermocouple installation. This is a view of the 4 interlocking sections of the phenolic asbestos ablation layer, which were also instrumented for heating measurements. Installation of some components in the reentry package, and the internal arrangement of the many items of instrumentation. Three radiometers recorded measurements through fused quartz windows. 2 total radiometers were located to measure total radiation near the edge of the front face and on the afterbody. At the stagnation region was located a combination total and spectral radiometer. The radiometers recorded measurements over the wavelength region from 0.2 to 4 microns, the transmission limitations of the fused quartz windows. Here are shown the 2 total and the total spectral instruments as installed in the package, and as seen during a quartz window installation in the ablation shield. As the life of the windows is short, radiative measurements are valid for only a short period following exposure of each shield. Data from the on-board instruments were telemetered to ground, air, and ship receiving stations in the reentry area in both real and delayed time. The delayed time transmission permitted recovery of data recorded by the reentry package during the period of high ionization. Data were also obtained by tracking optical instruments, infrared recording, spectrographic recording, radar, ballistic camera, and airborne optical recording devices in the reentry area. To place the reentry package in the proper attitude with the desired reentry velocity, a velocity package was designed utilizing an Antares solid rocket motor with a self-contained guidance and control system. The velocity package was programmed to orient the reentry package to a 15-degree nose-down attitude, spin to 180 revolutions per minute, and accelerate to 11,300 meters per second at the reentry altitude of 122 kilometers. This spacecraft combination atop an Atlas D launch vehicle was launched on a ballistic trajectory down the eastern test range from Cape Kennedy. The spacecraft attained an apogee of 835 kilometers and a range of approximately 8,400 kilometers, impacting in an area southeast of Ascension Island. animation describes the events. Following burnout of the launch vehicle, the spacecraft is separated and the velocity package guidance and control system reorients the spacecraft to the proper re-entry attitude. After coasting through apogee and upon reaching an altitude of 301 kilometers, the spin rockets are ignited, spinning the spacecraft to 180 RPM. The shell is jettisoned and the Antares 2 rocket motor is ignited to impart the desired re-entry velocity to the re-entry package. Following motor burnout, the re-entry package is separated from the spent motor and begins the experiment phase from 122 kilometers. The first beryllium calorimeter begins to glow and melts away. The first phenolic ablation shield is ejected. The second beryllium calorimeter melts. The second ablation shield is ejected. The third beryllium calorimeter survives the re-entry. The next sequence is an actual film of the Fire 2 re-entry on May 22, 1965, as seen from Ascension Island. The viewing time has been increased by a factor of 3 to permit recognition of events. First acquisition shows the gas light of the re-entry package and spent Antares as a single light source. The re-entry package now moves ahead of the spent Antares as the Antares begins to glow brightly and break up because of its tumbling action and the re-entry heating effect. The red glow behind the re-entry package is the melting of the first beryllium calorimeter, followed by ejection of the first phenolic ablation shield. The re-entry package moves out of the field of view to the left, leaving only a view of the disintegrating spent Antares motor case and adapter. As the camera again acquires the re-entry package, the second beryllium calorimeter is melting, followed by ejection of the second ablation shield. The low elevation angle restricts the view during the third data period. A still sequence of the first beryllium calorimeter melt is projected to permit viewing of the intense heating effects. The breakup of the spent Antares and adapter can be observed with objects which have a high ballistic number moving in front of other Antares components. This sequence occurred at an altitude of 60 kilometers and at a re-entry package velocity of 11 kilometers per second. These stills were selected from the second beryllium melting period and show the effects at the peak heating period of re-entry. This sequence occurred at an altitude of 46 kilometers and a velocity of 9.5 kilometers per second. Future space programs may now be planned with greater knowledge of the atmospheric heating conditions to be encountered during re-entry.